All right, so we're going to talk about some area. What does it mean to find area? Now, what's interesting is that when we start talking about area, the first thing we actually need to talk about is perimeter. And that seems maybe seem like a weird discussion to have, but it's kind of where we're going to start with this. So maybe it seems backwards. So yeah, this is white on white, so I do apologize about this, but I'm actually doing this for a reason. And the first thing I'm going to do is I'm going to just kind of trace this out. Now, in a previous video, we started talking about measurement, and I mentioned the idea that area is a two-dimensional measurement, frequently of a three-dimensional object. Talking about, like, say, how much area does my fence enclose for my backyard, or how much square footage of flooring do we need to cover our floor. The floor is technically a three-dimensional space, but what we're doing is we're covering the surface of the floor with something that is technically a three-dimensional object. So the flooring itself has three dimensions, but what we're referring to, the way we measure that, is just strictly on the square footage. How much space does it cover? What's the area it covers compared to normally because of the thickness of those materials is pretty constant, especially if you're talking about tile or engineered hardwood or just regular hardwood as well. But the thing that is also interesting is when we start referring to the perimeter of the space. Well, perimeter, remember, that's the distance around. So if we were to start, let's label these here, huh? A, B, C, and D. If I start at A and I start walking all the way around the rectangle, and I come back to A, how far have I walked? Well, we can get our ruler out, right? And we can measure this in centimeters because, hey, why not, right? And it works out to be, well, that's not quite nice, is it? But we can definitely do that. That is, what, 12, 12.9, 12.8? Let's go with 12.8 centimeters. It's kind of a bad angle. And then we have this next measurement here, which is 7.6 centimeters. And then the next one, which would be 12.8 again. Well, that's interesting, right? Well, it's not really because it's a rectangle. And if you think about our previous discussions about polygons, one of the things about rectangles is by definition, opposite sides have to be congruent. So that's actually a definition of a parallelogram. So all parallelograms, oh wait, we need to start the discussion on the other end of that, don't we? All rectangles are parallelograms, but not all parallelograms are rectangles. This is a parallelogram, this is also a rectangle. Okay, so the idea being here is here's the area. How do we find area? Well, area is defined as being length times width. But why? Why is it length times width? Now, come on, we could have measured this with inches as well, which you would have found that it's exactly 5 inches by 3 inches. It was a 3 by inch index card, so it's 3 by 5. So maybe we want to do it that way. Okay, so this is 5 inches, this is 3 inches. Does that bother anybody that 7.6 is equal to 3? No, maybe it does, maybe it doesn't. It's a different unit of measurement. So yeah, the numbers are going to be different. It's a different way of measuring it. It's like saying I have 2 soda cans or I have 24 ounces of pop. Well, which one is it? Is it 24 ounces or is it 2 cans? Well, if each can is 12 ounces, then those measurements are equivalent. 2 is equal to 24. But you need to make sure you're including your units there, right? So these are equal. But it's still length times width. Why is it length times width? Well, this is why inches in this particular instance is actually easier to deal with, because there's just fewer marks for me to make. And I'm just going to do this over here as well. I'm going to make a mark at the 2. Now notice what I did there. I broke it up into 3 sections. Now, I never claimed to be an artist, so you're going to have to work with me on my drawing here. Yes, I'm using a ruler, and I'm not sure the lines are completely straight. Close enough, though, all right? So once again, I'm going to measure out going across. Still 5, right? I'm going to do the same thing at the top. Anybody bothered by the fact I'm starting at 3 instead of 0? There's always somebody that's like, oh, why are you doing that? That hurts my head. Think about it for a second. You're still doing the same measurement. You're just starting in a different place. So if we go with this, and I guess I could have had this drown out in front of you rather than doing it while we talk, right? But I think there's some value in seeing it created in front of you instead of it just all of a sudden appearing. It gives your brain a little bit of time to process that. So notice what we now have. We have an inch that is 1 by 1 inch, right? Or a square that's 1 by 1 inch. And every square up there is 1 inch by 1 inch. So we actually define this space right here. That space is 1 inch squared. You say, why is it 1 inch squared? Well, because we define this area to be measured that way. Why do we define it to be measured that way? Because it makes sense. Because it's 1 inch this way and it's 1 inch that way. So what we've done is we've created a unit of measure here. We've unitized, and that's what we're talking about, we're doing here. We've unitized this space right here based on its characteristics. In this particular instance, we have one measurement this way and one measurement this way, and that creates a new measurement for us that we need to name. So we named it something, 1 square inch. That's what we named it. So here's 1, here's 1, 1. Like all these are 1s. How many do we have going across this way? We have 5 going across that way. So we have a length of 5, and we have a width of 3, or depth or height or whatever you want to call that, right? Which gives us 15 square inches. And that's the measurement of the area of that particular rectangle. It's 15 square inches because it's length by width. Because we created that many boxes as we draw it out, based upon there being 3 across this way and 5 across that way, or 12.8 and 7.6. And we still multiply those out and get whatever that works out to be. What is that? Something around 90-ish, right? So we still have, we'd have 90-ish equal 15. Those would be the same space using different measurements. And in that particular case, it would be square kilometer, square centimeters, square centimeters instead of square inches. But it's still talking about measuring that area. Now, what else can we measure? How else can we do that? How else is this useful? So what I did is I actually took that exact rectangle and I actually cut it. All right? Now, what's interesting or what's fun, some of you may not think this is very fun, is that when I do this, look what I've created. Yeah, that's right. I created a parallelogram with 15 square inches. Right? And you say, well, how do you know it's 15 square inches? Well, because all I did was just cut a piece off and I rearranged the same pieces. I didn't change the size of the pieces. So it's still the same pieces, just rearranged a little bit. So now it still has the same area even though it looks different. So it still has 15 square inches, which is pretty cool. All right, and we can rearrange this again. We could cut this again in such a way that we have a shorter parallelogram. But what is important to point out here is that we have the height times the base, and that height times the base is still 3 times 5, which still gives us an area of 15 square inches. And you say, well, okay, that's fine. That's dandy. What else can we do with this? This is something else. I'm going to take a trapezoid here, all right? And I've already cut the trapezoid in half, top to bottom, laterally right there from top to bottom. And I'm going to label this as base 1. I'm going to label this as base 2. And then, of course, this entire distance from here to here is the height. That entire distance is the height. All right? So if that distance is the height of said object, well, how do we find its area? Now, some of you may remember that a trapezoid has an area of 1/2 base 1 plus base 2 times h. I'm actually going to tell you that that formula is wrong. Some of you are like, what do you mean it's wrong? It's the one I learned in grade school. Yeah, I'm not saying that you did anything wrong. I'm saying it was taught to you wrong. Some of you are looking at that and saying, those are the same formula. And it's like, good, you understand the commutative property of multiplication. Good. But that's actually the formula. And I'll explain why that's the actual formula as opposed to this one. This one's the one that's written most of the time, but this is the actual formula, and I'll show you why. So if this is the height, and I'm going to cut it laterally, I would cut it in half. I have half the height, right? Look, I have two trapezoids that are now half the height of the original trapezoid. Well, that's boring. I'm going to do this. I'm going to flip one of the trapezoids upside down. I'm going to stick them end to end. Look at that. We have a rectangle with one measurement of 1/2 of h, and we have another measurement of b1 plus b2. There's the area. Length times width. So the width is 1/2 of h, and the length is b1 plus b2. We could do it the other way too, just to point this out, that we also have a parallelogram, well, which has the exact same formula. So you still have length times width. It's still that same measurement. And I'm only doing this to point out that every time you find the area of something, that's what you're doing. You're finding the length times the width. Even with a circle, that's what you're doing. You're like, how do you do that with a circle? That doesn't make any sense. Well, actually it does. The idea behind a circle, well, there you go, right? What's the area for, how do you find the area for pi r squared, right? Well, actually, you know what I'm going to do? I'm going to leave this one to you to investigate a little bit. I'll see, I might create another video for you, but that's the area formula for it. And you're still doing length times width. I'll let you play around with that and figure out what I mean by that, but you're still doing length times width. You can do a little bit of investigation there with it. It's kind of cool. All right, so that's area. So what else do we have? Well, we also have surface area. Well, how do you figure out the surface area? Well, the first thing we need is an object that is not 3 dimensions, right? So actually I have this cube here. Now what makes this a cube? Well, the reason why this is a cube is because you have a square and a square making up all the sides of the shape here. And if any one of these sides was longer than the ends, you'd have a rectangular prism. And if none of the shapes were the same length or measurement, but they were all equivalent, parallel-wise, you'd have a rectangular prism again. But what's surface area? Surface area is actually the individual sides all added together. And this one's fun because I can actually take out that internal shape there, which is still a rectangular prism. This particular prism is special in that it's regular and it becomes a cube. But I can actually unfold this one and notice what I get. So when I talk about surface area, I'm talking about side 1 plus side 2 plus side 3 plus side 4, side 5, and side 6. I need to add all the sides together. This one's easy to do because all the sides are the exact same thing. But if they weren't, we'd find the area of each individual side and we'd add them together. All right? That's a little bit more obvious when you deal with, say, a triangular prism, right? Well, this one's a little different. The ends are triangles, right? And the sides are rectangles. And when we unfold it, what do we get? Well, we get those 3 pieces, which look like they might be the same side, but again, we find the area of each individual piece, find the area of the 2 triangles, and we add all of them together, and that gives us the surface area. So some of you were waiting for me to write down a formula for the surface area. So here it is. Area for the surface area. Surface area is the sum of the area for the sides. And I know what some of you are thinking. That's a horrible definition or a horrible formula rather, because that's actually just nothing more than a definition. Yes, it is, because I can't give you all the formulas for surface area. Each one is going to be dependent entirely upon the shape itself. Because just to kind of give you an example, here's a third one, and I actually have more than that. I'll show you the other shapes. But here is a circular prism. Now, some of you are like, no, that's a cylinder. Well, the end is the circle, right? And then the sides are more or less straight based upon that. Think about this. What made this a triangular prism? It was because the base shape was a triangle, and then you simply just repeated triangles all the way to the other end of the object, however far that was. That's what made this a triangular prism, is that from one direction it just looked like a prism, and then from the other direction it just looks like a rectangle or whatever. You say, well, that doesn't look like a rectangle. Does it not? What's the real shape from that perspective? What does it really look like? You say, well, it looks like a circle. That doesn't look like a circle to me. Not from that perspective. This perspective, it looks like a circle. That doesn't. If this were a slice of bread and I were to cut it this way, going across, parallel to the page, my slice would be a rectangle. All right? So anyway, so we take this and we unfold it. Actually, I'm going to unfold it that way. And look what we get. We get a rectangle and two circles. Wow. Isn't that neat? Looks like something staring at you, like a bug or something like that, right? And then once again, it's the surface area is strictly talking about the sum of all the sides. One of the sides, that's interesting, isn't it? One of the sides is a rectangle, and the other two sides are circles. So you find the area of the circles, you find the area of the rectangle, and you add them together. So that's why I'm harping on this particular aspect when you talk about surface areas. The way you find surface area is to find the individual pieces and add them together. Okay? So I hope this is helpful. Please reach out with questions and comments. Otherwise, just enjoy doing some math. Take care.